Only a little bit? Okay. So today we are getting started with angles. A lot of this will be review, and for that, I'm only mildly sorry. Because it turns out some of you actually need review on what an angle is and what a triangle is and certain types of triangles. Yeah. Okay, so we're going to start off with some vocab and some nice pretty pictures so that you cement this into your brain somewhere. So the first thing is an angle. Trigonometry is all about finding ratios associated with a specific angle, and when that angle changes, the ratios change. So we first have to know what an angle is so that we can start the ratios for those specific angles. An angle is a set of points determined by two rays having the same endpoint. So if I were to draw a picture of an angle, I would have one ray, two rays, and then the angle formed by the distance between those two rays at any given point is an angle. When we talk about angles in trigonometry, we typically talk about it in terms of theta, which is a circle with a little line through it. This stands for some unknown angle, okay? We can also name angles based off the points that create it. So for example, if one of my rays had the point A, if the angle itself was point B and my other ray had the point C, I could name this angle as angle ABC or angle CBA. It always has to go in order. Whatever point is at the angle or the point where the two rays meet has to be in the center when I'm naming it. When we have an angle formed by two rays, there's something very unique about those two rays. So I'm going to draw another one just so we can see.
It would be nice if I could see it.
Wouldn't it really? Super duper nice. What if I blew it up like that? That help? Okay, awesome. So let's say that I have this ray. This angle. This ray right here is called our fixed, fixed or initial side. This is the side where my angle started, and then where my second ray moved to created the measure of the angle we have between them. So this one is fixed. It is unchanging. The one that changes, however, is called the terminal side. And then the point where these two rays meet is called the vertex.
How do you determine which?
This one's always going to be the fixed one, as far as we're concerned. Yeah, because we're going to be talking about it in terms of a circle here soon. So this one is always fixed. This is the one that changes. A lot of times you're also going to see an arrow or a curve with an arrow drawn inside of the angle. That also indicates that my angle started here, which means this is the fixed side, and this one that moved, which the arrow is pointing to, is our terminal side. That's another way of knowing. So because we have angles that are determined by this fixed and terminal side, we have something called coterminal angles. And coterminal angles are angles that have the same initial and terminal sides. But different angle measures. Before we get into how to find other coterminal angles, we're also going to identify what a straight angle is. Anybody remember from geometry? Nobody?
I've never taught this.
What is a straight angle?
Ways.
It's a straight line. It's 180 degrees. So glad I'm meeting that. Okay, so a straight angle is an angle whose sides lie on the same straight line but extend in opposite directions. This is also a 180 degree angle. So if I were to draw a straight angle, if I had my vertex and I had my fixed side, to be a straight angle, my terminal side would have to lie on that same horizontal line as my fixed side, but extend in the opposite direction. So that would be a straight angle. Outside of coterminal angles and straight angles, we also have quadrantal angles. And these are angles whose terminal sides lie on an axis. So if we think about a coordinate grid, and if we say that this right here is my fixed side, I'm going to say F for fixed. If I had a terminal side that lied along my y-axis, that would be a quadrantal angle. If I had a terminal side that lay, I'm not really sure, that was along my y-axis going in the opposite direction, so 180 degrees, that would be a quadrantal angle. Okay, or if I had a terminal side that lies along my x-axis going down, it's still along the x-axis, which makes it a quadrantal angle. So it lies along the axes where my quadrants separate themselves. Remember, this is quadrant 1, 2, 3, and 4. So if it lies along my axes, it's a quadrantal angle. Okay? That's a fun word to say. And then we know from geometry that if it lies along the y-axis going up, that's a 90 degree angle. If it lies along the x-axis going left, that's a 180 degree angle. And then if it lies along the y-axis going down, that's a 270 degree angle, right? Because each quadrant is 90 degrees. So that's just helpful information in there as well. Yes, Colin?
Why is it not 90?
It could be. And that's what we're going to get into next, which is positive and negative angles. You can thank Colin for that.
How can an angle be negative? If you're going the opposite way, it's still an angle.
Not according to our lovely coordinate plane. So Colin posed the question, why would I measure this, so right here, as 270 rather than 90 going the opposite direction? That's because the direction of which your angle opens indicates whether it's a positive or a negative. So if it opens up, it is a positive angle. If it opens down, it is a negative angle. So this 270 degree angle is equivalent to this negative 90 degree angle. They coincide, but they technically have different angle measures. So positive and negative angles, we're just going to do a couple examples so you can kind of see what I'm talking about. We always assume that this right here is our fixed side for an angle that is unchanging at this point. So if from this fixed side, I have a terminal side that extends down here, that would be a positive angle because from the fixed side, it opened up. And then I would just measure this to be, 225 degrees. That's not important. The important part is that it is positive angle. If I had another angle from my fixed side that opened up there and the indicated direction was that it opened up first, would that make it a positive angle or a negative angle? Positive, because it opened up. This tells me that from my fixed angle, it went up and then around, which makes it a positive. Let's say I have a third angle that from my fixed side opened down. Is that positive or negative? Negative. So the direction of opening indicates whether it is a positive or a negative angle measure. Every negative has a corresponding equal positive measure. Every positive has an equal corresponding negative measure. Okay, so the example we had before was 270 degrees. Positive or correlates to a negative 90 degree angle measure. Okay, so they can coincide, but they technically have different measures. Make sure you're keeping that in mind. So then each of these angles can not only be defined as a positive or a negative, but we can actually measure it as well. So for these, we would have to approximate because we don't really have a compass in front of us to figure it out, or a protractor. But we know that each of these is a 90-degree difference. And we know that a full circle is 360 degrees, right? That's a geometry piece of information that's in our brain, which means halfway between each of these 90-degree differences is a 45-degree angle. I gotta think about that. 315? Yeah. We don't just break it down though into quarters like we see here. We can also do thirds. So if you look at a unit circle, which is what we're going to be calling this in the future, you would also see that we can find a common 30-degree angle and 60-degree angle on each of these quadrants as well. So we break each of these quadrants down into halves, into fourths, and then into thirds. And we can break it down farther to 6th and 12ths and 24ths and keep going on. The common ones, though, are the third measures and then the half measure. I'm not going to make you fill this entire thing in because we're going to have a unit circle for you to do that with. Just know that we use these to indicate what our angle measure is. Okay? But again, you should have been measuring angles in geometry sometime. Did we? Okay, just check it. I didn't see a whole lot of response from this side. Did we measure angles in geometry? Okay, we might have to practice that just to do it. Okay. A straight vertical line? Well, assuming that our fixed point is always here, we can't have a straight vertical line.
And the terminal have the same angle, does that mean the positive and negative?
If they're the same angle?
You said that the coterminal has.
Oh yeah, we're gonna get there in a second. We're gonna get there. You're just all about jumping ahead today. Actually, that is literally what we are doing next. Okay, so on our circle, we talked about something called coterminal angles. These are angles that have the same fixed side and the same terminal side, but have different angle measures. So essentially, it means that I have two angles that both look exactly the same, but have different angle measures. So I have to ask myself, how is that possible?
One opens down.
Okay, that could be. We could have one that opened into a positive angle and one that opened into a negative angle. But let's assume they're both positive or both negative. How is that possible?
Oh, is it like the scale perhaps?
Nope. Am I limited to only going around this coordinate plane once? So can I only have a measure that's less than 360 degrees? No. I could complete as many trips around the circle as I wanted to. And every time I do, it adds 360 to my angle measure. So for example, we would say this is a 45-degree angle. On this one, let's say that before stopping at that angle, it went around once completely. So that is not a 45-degree angle because it made one full rotation first. I have to add 360 to it, which means instead of that being a 45-degree angle, that's a 405-degree angle. But it still has the same fixed side, and it still has the same terminal side. So to find co-terminal sides, we can add 360 as many times as we want to. So I could have it go around another time, and I'd add another 360 to that. I can also subtract 360 from it to find other coterminal angles as well. Okay, so Gabe did point out that if I had a 45-degree angle here, it would have a coterminal angle that was just a negative measure that ended in that same point, which means it would be 45 minus 360, which makes it a negative 315-degree angle. They have the same fixed side, and they have the same terminal side, but they have different angle measures. So we generalize and say to find all coterminal angles, any angles coterminal to theta, we add or subtract multiples of 360. Because we add or subtract multiples of 360, there are an infinite number of angles that are coterminal to any given angle theta. Because I can just keep subtracting 360 or keep adding 360 and finding new coterminal angles that have the same fixed and terminal points. So of course we're going to practice this, but does this kind of make sense to everyone about why they are the same point just with a different angle? Everyone okay with that? Okay, so let's say, for example, instead of having a graph here, I just went ahead and told you to find 3 angles that are coterminal to let's say 115 degrees. On your own, I want you to find 3 angles that are coterminal here. Try to find 2 that I'm pretty sure everybody's going to find, and then try to find a third one that you don't think anybody else will get. So I want 3 angles that are coterminal to 115 degrees. This might end up being a 3-day lesson. Cody, tell me how you found one angle that was coterminal to 115 degrees.
Added 360.
Added 360 to it. Perfect. That's probably what most of you did, right? So when we do, we get 475 degrees. Who else had 475 as one of their coterminal angles? Perfect. Ray, how do I find another coterminal angle? Well, 115 is the one I started with, so I can't use that one again. Subtract 360. Adding 360 and then subtracting 360 is the easiest way to find two of them. So we have 115 minus 360. When I do that, what do I get? Negative 245. Okay, so we found two. Somebody tell me how you found a third one. They're an infinite number, so there's, as long as you did the math right, there's no wrong answers. Yes, back up. Okay, so in other words, you took our original angle and subtracted 2 times 360, which makes it 720, right? Okay, so what did you get when you did that? Negative 605 degrees. Anybody else have that one? No? Okay, that is correct. So you could also think of it as the fact that I subtracted 360 from this, which means I could just find another angle that's coterminal to the negative 245 and subtract 360 to get to here. And we could subtract 360 again if we wanted to find another one. Or we could have gone to 475 and added 360 to that and gotten what, 835? Anybody get that one? Okay, a couple of you. Or you could have done 360 times 10 and added or subtracted that to 115. There are an infinite number of coterminal angles to any given angle theta. Okay, so don't think just because nobody else got that one that's wrong, because it's not, as long as you did the math right. Anybody have issues finding angles coterminal to a given angle? No, we're okay. Fantastic, let's move on. Our last little bit of review are the different types of angles that we can have. So the first one is an acute angle. What is an acute angle?
Angle less than 90 degrees.
Okay, so because we also have negative angles here, we need to clarify a little bit better. An acute angle is any angle between 0 and 90 degrees. So greater than 0 but less than 90. Because technically negative 115 is not an acute angle. We can also have an obtuse angle. What would be an obtuse angle here? Greater than 90, but less than 180. So an obtuse angle is any angle between 90 and 180. We also have complementary and supplementary angles. So complementary angles, we're going to just call them A and B, are angles such that A plus B is equal to 90 degrees. So complementary angles add together to equal 90. Whereas supplementary angles add together to equal what? 180. Questions, concerns, or issues with any of that?
What if it's above 180?
Then we have a different name for that that we're not going to get to yet. No, because for the majority of the time, if we're talking acute and obtuse, it's a positive angle. Or it can be rewritten as a positive angle. So it's not that important. The majority of what you're going to have to remember from this are these two, complementary and supplementary angles. So before we can actually do anything with complementary and supplementary angles, we need to identify the different ways that an angle can be measured or written, okay? So obviously we are most familiar with angles written in degrees, right? That's what we are most familiar with. But there are actually at least two other ways that we can write and express an angle measure. The one that we are going to look at right now is going to be degrees, minutes, and seconds. Before we do the conversions, we're actually just going to identify what portion of a degree a minute is and what portion of a degree a second is. Okay, and then we're going to do some stuff and then we're actually going to convert it around. So we already know degrees, right? Those are the whole number measure that we got. A minute then is 1/60th of a degree. We could also say that 1 degree is equal to 60 minutes. So if you really, really have trouble thinking about it, we can imagine our degrees are our hours. And then a minute is 1/60th of an hour, which means a second is 1/60th of a minute, or 1/3600th of a degree, or an hour, depending on how you want to think about it. And another way of thinking about that or writing it is that a minute is 1 apostrophe. So 1 minute equals 60 seconds, which would be a double apostrophe. So when we're talking about degrees, minutes, and seconds, 1 degree is equal to 60 minutes. 1 minute is equal to 60 seconds. Okay, or 1/60th of a degree is equal to a minute. 1/3600th of a degree is equal to a second. I know that sounds really, really confusing, and it takes a second to process it, which is why we're not immediately doing the conversion. But it should make more sense when you see some actual numbers in front of you. So before we do the conversion and kind of confuse the heck out of you, we're just going to practice complementary and supplementary angles given non-whole degrees. Okay, because that's sometimes extremely helpful here. So let's say that I would like to find an angle that is complementary to a given angle theta. So this is an example that's going to be using degrees, minutes, and seconds already given to us. So we're going to be doing 2 of these. For the first one, which we're going to label A, let's assume that our angle is equal to 25 degrees, 43 minutes, and 37 seconds. And I would like to find an angle that is complementary to that. So complementary angles have to add up to what? 90. So essentially what I need to do is I need to take 90 degrees and subtract this number from it to get an angle that's complementary to it. However, I need to have minutes and seconds in this number as well so that I can subtract the numbers and seconds that I have in this angle, which means I need to re-represent 90 degrees in degrees, minutes, and seconds. Anybody have an idea of how we're going to do this?
But it's like 89.
Yeah. So instead of 90 degrees, we're going to have 89 degrees, 59 minutes, and 60 seconds. Because 60 seconds is 1 minute, which will add to this, which will make it another whole degree. So I just took 90 and I split it up so I had degrees, minutes, and seconds present to do the subtraction with. So now I'm going to take this 90 degrees and I'm going to subtract from it the 25 degrees, 43 minutes, and 37 seconds. And we subtract just like normal. And we should end up with 64 degrees, 16 minutes, and 23 seconds. Just like we would if we were doing subtraction where we had to borrow. If I ran out of seconds here, I would borrow from the minutes in front of it. If I ran out of minutes, I would borrow from the degrees in front of it. Okay, so 1 minute would add, taking 1 degree here would add 60 minutes. Taking 1 minute here would add 60 seconds. So we just borrow from the one in front if we have to. So the complementary angle that we found is the angle that is 64 minutes, 64 degrees, 16 minutes, and 23 seconds. Anyone have any major issues with that? For the most part, is that okay? So the hardest part is just trying to reconfigure what we know 90 degrees as in a different format. And then from there, it's just basic subtraction. We're, for the most part, okay. So let's say that instead of being given to us as degrees, minutes, and seconds, let's say that our theta was given to us as a decimal. So let's say I have 73.26 degrees, and my goal is to find an angle that is complementary to that theta. Complementary, again, means that it adds up to what? 90. But I can't just take a whole number and subtract a decimal from it unless I have decimals in my whole number as well. Which means I just have to take 90 and rewrite it so it has the same number of decimal places as the number I'm subtracting from it. Clearly, I can't do 0 minus something, so I'm going to have to borrow from the 9 all the way down to the last 0. Hopefully, we remember how to do this. And then we just subtract. And when we do, we end up with 16.74 degrees as our complementary angle. Questions, concerns, or issues there? We're going to do one more thing and then we're going to stop because I can already see that your brains are fried. Everybody get that written? Everybody kind of understand how we did that? You would do the same thing then with supplementary angles. If I had to change 180 degrees into degrees, minutes, seconds, it would be 179 degrees, 59 minutes, and 60 seconds, just like we did for this one. Okay? So as I said before, there are 3 primary ways that we can measure angles or express an angle measure. Degrees, which is what we've already worked with. Degrees, minutes, seconds, which we briefly introduced here. And the last one is radians. If you've taken physics, you probably have done a lot with radians. Okay? Degrees and radians are our primary angle measures. Just know that degrees, minutes, seconds are also important. So another way to measure an angle is with radians. A radian, because vocabulary is important, is a measure of the central angle subtended by an arc equal to the radius of the circle. So I know that sounds extremely confusing. So I will draw a picture to make it hopefully make a little bit more sense to you. So in theory, this means if I have a circle that has a radius of r, oh, that's really bad. And I have an angle, I don't know, that looks like this one. It's basically saying how many lengths of r are present on the arc that corresponds to that angle. So that number of radius length is the number of radians I have in my angle. Okay, so the radius of my circle is the measure we use to divide up this arc length. However many radius measures I have is the radian measure of my angle. Of course, we're not going to have to draw something like this every time because that would be exhausting, like truthfully. So there is another way of kind of recognizing radian measures in terms of degrees. So the most common one is that 180 degrees corresponds to pi number of radians.
Oh, we did it that way.
Yes, we do not use the 53 because we don't. That's cheaters. Plus, it's rounded, so it's not an exact value.
Did he say that the same thing about the
Yeah, he said mathematicians like it this week because they're lame.
We're not lame. We like exact values, not rounded numbers.
That's actually what he said. But
Yeah.
I put in.
Wow. Thank you, Dave. Thank you. Okay, so if 180 degrees is equal to pi, so 180 is half my circle. Remember, that's a straight line. What do you think 360 degrees corresponds to? 2 pi. Those are the most common 2-degree radian conversions that we recognize without doing any work at all. So because we know that 180 degrees is equal to pi radians, it actually allows us to find a constant that we multiply to convert between radians and degrees and radians. Okay? So the constant is that 1 degree is equal to pi over 180 radians, which is approximately 0.0175 radians. And 1 radian is equal to 180 degrees divided by pi, which is approximately 57.2958 degrees, which is the conversion you guys use in physics. We do not use those decimals because those are rounded values that after a while will throw off the actual value that we would calculate. However, if you're in a pinch and can't remember what we would multiply to do the actual conversion, this will get you close. Okay? Okay, so I think I have enough time to actually introduce the conversion, and then I promise we're done. We're not going to do anything with it. So these things right here are actually what we will be multiplying by to do the conversion from degrees to radians and the conversion from radians to degrees. So I'm going to use D and R to represent degrees and radians respectively. So if we are converting from degrees to radians, so that's D to R, the number of radians we have is equal to the degree times pi over 180. And that will tell us the radian equivalent to the degrees that we started with. If we're going the opposite direction, however, so if we're going from radians to degrees, then the degree equivalent would be equal to the radian times 180 divided by pi. If you ever can't remember the order in which this 180 and pi has to be written, whatever notation I want to end up with has to be on top. So because I wanted radians on this one, the pi had to be on top in the fraction. Because I wanted degrees on this one, the 180 degrees had to be on top in that fraction. It's always 180 in pi, you just have to remember which way it goes. And then this is where we're gonna stop. We'll actually do the conversions tomorrow. So this seems like as good a place as any. So your homework is on Canvas. You obviously can't do all of it, but you can definitely get a look at it and see if you can work on some of the problems